In today's economy, cash flow is tight, and families are held captive to high interest rate credit card debt. Churchill Mortgage can restructure your current mortgage and significantly reduce these problems. Get a free analysis and learn how to eliminate credit card interest rates, lower bills, and start taking control of your budget. Get started at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us. This is Space Nuts. It's all about astronomy and space science. We talk about what's happening on Earth and in heaven and everywhere else, because we've just got such a wide scope of places to investigate and talk about. I mean, it's limitless, really. And on the program today, we will be discussing some work that's been done through the University of Cambridge, where they may have accidentally stumbled across evidence of dark energy. Now, we know it exists. We know it makes up a substantial part of the universe. We've just never been able to actually identify it directly. So have they found dark energy? Have they found evidence of it? I mean, we know it's there because of the influence it has. So we'll look into that. We're also going to talk about a 2,200-year-old observatory in Peru. It was only recently discovered around 2005, and it still works. It still works. Quite extraordinary. Plus audience questions. We'll be talking about whether or not you can watch light move through the universe. If you're at the right place at the right time and a star suddenly appears, could you watch the light moving across the universe? And a bit of a tongue-in-cheek question about flat Earth theory. Also looking at the effect on non-moving objects in the universe. Can anything stay still? That's a good question. And a question about time and gravity, all on Space Nuts this week. I'm your host, Andrew Dunkley, and joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew. How are you doing?
I'm quite well. How are you?
Yes, very well indeed. Thank you.
Coping with lockdown still?
Yeah. More or less. We are
Yes.
still locked down, that's right. But,
well, at least this gives us something to do.
Yeah, it does. Actually, lockdown, the antidote to lockdown is that we've got 3 beautiful planets in the night sky at the moment in the early evenings. Venus, actually Mercury's there if you get it in time before it sets in the early evening, but also Saturn and Jupiter. I had the telescope out at the weekend having a look. They look stunning.
Yes, I've seen quite a few photos that people put on the Space Nuts podcast group Facebook page when they go out observing. So quite a few of our listeners have got telescopes, and they've taken some amazing shots lately. So
indeed,
pretty impressive. And I believe Jupiter took another hit the other day.
Indeed, yeah, I was just going to mention that. That's right. And that was captured by a number of amateur astronomers taking videos of Jupiter, and they got this bright flash not very far from Jupiter's equator. It was recorded by several astronomers, so it wasn't a glitch in the, detector or anything like that. Great stuff. It was something big hitting Jupiter's atmosphere. Probably a small asteroid.
An asteroid or a comet, maybe a comet.
Yeah, maybe a comet.
Who knows? Yeah. They might figure it out. They might not. But it was quite a flash. Now, let's move on to our first topic, Fred, and that is dark energy. We get so many questions about dark matter and dark energy, all because of the mystery surrounding this stuff. Dark energy, we talked about how it's probably not well named, but they've been doing some experiments through the University of Cambridge, and it looks like they might have stumbled across the detection of dark energy. It's not been absolutely confirmed, but they might have, tripped over it by accident because they were trying to do something else.
They were, that's right. So this is an experiment at the Xenon 1T facility, which is at Gran Sasso in Italy, and it's a bit like an astronomical telescope. It's built as a facility that can be used by many astronomers, and they all come and get there 2 or 3 nights or whatever it is on the telescope, and then go away and work out their results. And a facility like this is similar in the sense that it has accessed by various different researchers. And in this case, as you've said, these researchers are from the University of Cambridge. And they've got, basically, the bottom line, Andrew, is that there are some unexplained results that have come from this experiment. What these scientists were looking for was evidence of extremely rare interactions between particles of dark matter, which makes up about 27% of the mass energy budget of the universe, compared with about 5% for all the stuff we can see.
Yeah.
So they were looking for, so we think that dark matter is some species of subatomic particle which we haven't yet identified, but that it may, on very rare occasions, interact, i.e. bash into a normal matter particle, hydrogen or carbon or whatever. The idea of this Xenon 1T experiment was to try and detect such collisions. But what they found was a background signal that didn't match any of the predictions for dark matter, but actually was more like the kind of signals that you might expect from dark energy. And that's intriguing because dark energy has always been seen as the harder problem to solve. It's, 68% of the universe is dark energy. And it's basically an energy of space itself. That's what we believe that's causing the expansion of the universe to accelerate. But subatomic physicists, they think in terms of dark energy as being carried by particles. For example, gravity, which is in some ways the opposite of dark energy because it's a pulling together of matter, and we do understand gravity. That we don't have a subatomic model for it properly yet, but people speculate that it's carried by gravitons, subatomic particles that carry the effect of gravity. And there may be particles that carry the effect of dark energy. And that's what they think they've detected. You know,
it's really funny because when I was reading the article, a thought popped into my head and I thought, is it possible that dark energy is simply anti-gravity?
No, it's not.
Okay.
And the reason for that is dark energy is everywhere. And the effect of gravity is well understood. It follows the inverse square law, so that, as you move away from it, the gravity drops off with the square of the distance. Dark energy is not like that. It's everywhere.
Yeah.
So it is different, but its properties are similar in the sense that if gravity is an attractive force, if I can put it that way, dark energy isn't. It's a repulsive force.
Yeah, so in that way, they seem to be opposites to each other in that respect.
That's the thing. But it's not anti-gravity, because to have gravity, you need matter, and we don't seem to need matter for dark energy. It's just there.
Okay. Wow. And they're going to do some tweaking of the experiment, as I understand it, to see if they can now hone in on this, because it's not absolutely certain that this is what they've discovered, is it?
No, that's right, and these things never are. They're what you have to do. You get something that looks suspicious, and then you, exactly as you said, you home in on it to try and really kind of tease it to death to find out what's actually lurking there, whether it is a real observation or something different. And a classic example of that was a couple of years ago. There were 2 experiments at CERN that gave results that suggested that a subatomic particle had been discovered that might lead to the proof of supersymmetry, which is another theory that doesn't have any physical observations behind it at the moment.
Yeah.
But both of those observations, even though they were done on 2 different instruments, they disappeared. When they looked more closely, the signals weren't there. And I should explain that this is all measured in terms of probability, what the probability is of this being real. And for it to be reported as a real effect, it needs a very high probability indeed.
Well, they're going to try and replicate this. And the part of the story that really made my eyes pop out was, we think we might be able to get an answer within a decade.
Yeah, that's pretty soon for this sort of thing. Yeah.
I guess so. All right. Something to watch with interest, and may slow down the number of questions we get about it.
Well, it will be. Yeah, wouldn't it be great if we could pin down dark energy? And what will be even greater is that really will be new physics. So it's beyond the theory of relativity, and that could open up all kinds of possibilities.
Yeah, couldn't it? Wow.
Yeah.
Okay, now let's talk about this Peruvian observatory that was discovered in 2005 and has hit the news again. What's the story with this one, Fred?
Yeah, this is something very, very close to my heart, Andrew. And the reason is that Marnie and I led, I think, the first tourist expedition to this site back in 2007.
Wow!
It was our first science tour. And we had one of the archaeologists who was responsible for the discovery, Ivan Getzi, Peruvian scientist. He came with us. So we got a first-hand look at it. And honestly, it is such a haunting place that it's stayed with me ever since. If anybody's interested in following up my experience in that, I think it's chapter 3 of Star Craving Mad. My book about astronomy travels is devoted to this place and what it was all about. So what we're talking about is this is about 370 kilometers north of Lima. It's in the Casma Valley is the river valley name, and this is a place where a river flows down from the Andes, and of course it comes and goes very strongly with the snow melt in the Andes,
right?
And huddled around the river are fertile areas with little villages in them, but also so you only have to walk 300 or 400 meters away from the river, and you're in desert, and it's proper sandy desert.
Yeah, I thought from the video it looked really desolate.
It is utterly desolate, but at the same time, 2,300 years ago, and in fact, at least 1,000 years before that, because there are other artifacts there, it was a thriving centre of population with probably a religion that demanded huge constructions, and there's evidence of plazas on a mammoth scale, 0.5 kilometre across, and other structures having been there. But in the middle of all this, there's a hill which runs north-south, pretty well exactly north-south, almost like a Hog's Back type hill, with a curved top. It's 200 or 300 metres long. And on top of that are 13 towers built to very exact proportions. They're damaged now. Earthquake damage tends to knock the corners off structures like this, so most of them have got some earthquake damage. But those towers have actually been known for many decades, but it was only in 2005, as you said, and actually published in 2006, that Ivan Getzi and another well-known archaeoastronomer, that's the ancient astronomy, who's at the University of Leicester, Clive Ruggles. And I was actually talking to Clive last week because he did a talk for us. A great speaker and a great scientist as well. So Ivan and Clive figured out that what these towers were for was a calendar, essentially. So what you've got is they identified 2 places, one to the east of the row of towers, one to the west of it, where if you observe the sun rising on one side and setting on the other side, those towers act as a kind of calibration of the horizon. So the sun comes up slightly differently every day.
Yep.
And by looking at where it crosses those towers, you can see exactly what the date was. So an enormous amount of effort went into understanding that and building it. And we're left with this record of a civilization about which we know very little. They're well pre-Inca. The Incas were in the 14th, 15th centuries, 15th, 16th, I think, actually. But this is a different civilization. What is really striking, though, is that you could, if you make your observations carefully, you could work out what day it was within a year. Now, they didn't have a modern calendar then, but they would have perhaps worked out the dates by when the sun crossed this. They crossed the different towers. And what it seems to have been all about, Andrew, and this is the slightly gruesome part of this, was ritual warfare.
Oh.
It was about the gods telling them that they had to go and beat up the neighbours because they'd get the water if they didn't. And they had these ritual wars which were absolutely scathing. They were ghastly, gruesome. There's another temple not very far from Chanquillo, which we also visited, that's full of carved murals that look as though they've been made yesterday. This is more than 3,000 years old.
Amazing.
But it shows dismembered bodies, and it's just very accurate and really grim to look at. So that was what it was all about, which is bizarre to our understanding, but it's an extraordinary thing. The reason why it's in the news again, Andrew, to get to the point, is that it's just been given World Heritage listing.
Oh, and so it should.
Yeah, thanks to Clive and other people. It really needs protection. It is such an iconic site.
Magnificent. It must have been a thrill to get to see it.
Unbelievable.
Yeah.
Yeah, unbelievable.
Amazing. All right. You can learn more about it by jumping online. There's lots of articles, and it's easy to find. I think the University of Leicester has published a story about it as well. So, go and dig that one up. You're listening to Space Nuts. My name's Andrew Dunkley with Professor Fred Watson. Now, let's take a little break while I tell you about our sponsor, NordVPN, and a special deal available to you as a Space Nuts listener. Now, NordVPN is providing what's known as a virtual private network, and it secures your internet service. Basically, you sign up to the internet through whatever provider you use, and that doesn't save you from exposure to cyber criminals and all sorts of other nasties. People in governments around the world sometimes like to keep an eye on what you're doing, and you may not like that. With a virtual private network, you can basically build a little wall between your provider and what somebody might be trying to figure out in terms of your online activity. So a VPN is basically a way of protecting yourself from people knowing what you're doing. It also protects you from criminals and from all sorts of surveillance through an encrypted tunnel. And that just means no one can get their beady little eyes on what you are doing. And that certainly protects your bank accounts. If you do online banking or online shopping or anything like that, a VPN is a great way of keeping yourself pretty well enclosed and no one can get near you. It secures all sorts of devices as well. It'll secure a Windows computer, a MacBook, anything with a Linux operating system, Android, Apple. And with this deal, you can secure up to 6 devices on a single account, including your router, most important. Now, it'll also enable you to log into a server in another country and watch TV shows via some of the online services that you can't access from your home country because of geolocation, geo-blocking, whatever you want to call it. It happens all over the world. I've had it happen to me a few times. Sorry, you can't watch this. You're not in the right geographic location. So you log on to a VPN in that country and yes, you can. There's 24-hour, 7-day-a-week support. It's the best VPN in the business, and it's certainly not the most expensive. There are others out there that aren't as good that'll cost you more. Now, with this deal that they're offering to Space Nuts listeners, it's a simple case of logging on to a special URL and you can learn all about it. But the deal is a 2-year plan plus 4 months free with a 30-day money-back guarantee. If you're not happy, you can give up the deal and nothing will be asked. A 2-year plan plus 4 months free. And to take advantage of this deal, just log on to nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. NordVPN comes highly endorsed. I've been using it quite a bit lately, and it does not slow your system down. In fact, it sometimes makes it faster. I still can't figure out how that works technologically, but I don't care. It does. And it's been endorsed by some pretty significant organisations, including the BBC, TEDx, Forbes, the Huffington Post, Wired, BuzzFeed, they all have very positive things to say about NordVPN. So grab the deal. Jump online and look at the special URL, nordvpn.com/spacenuts, nordvpn.com/spacenuts. Check it out. It'll cost you less than a cup of coffee per month. So have a look at it today, nordvpn.com/spacenuts. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Thanks for joining us on Space Nuts. Now, Fred, because we've received so many questions in recent times, we're going to do a bit of catching up. But this one came in via email from Trevor in Victoria. Hi, Andrew and Fred. I have a question about light and if we can see it. Light is said to be the fastest thing in the universe, travelling at about 300,000 kilometres per second. But given the size of our galaxy, let alone the size of the universe, this speed seems to be quite slow to me. Therefore, I was wondering if we were looking hundreds of light years out into space and let's say a new star suddenly started to shine, would we be able to see its light travelling through space at right angles to us? I expect it would need to be reflecting off dust clouds for us to see it, but from such a distance, it would seem to me that the light would appear to be travelling rather slowly across space. Thanks, Trevor from Victoria, Australia. I think I understand what he's saying. So we're out in space and we're looking over there and a star appears. Could we watch the light traverse the universe at 300,000 kilometres per second, give or take?
And yeah, the answer is yes. Trevor's given an absolutely picture-perfect definition of what we call light echoes, because exactly that phenomenon happens. And so in a typical situation is a supernova explodes, a star that gets to the end of its life, it detonates, it has an enormous light output, becomes very bright for a relatively short period, weeks or months in different circumstances. So what you've got is this expanding shell of light centered on the supernova, all traveling outwards in all directions at 300,000 kilometers per second. And it's well defined because it's got a sharp front edge where the supernova switched on and a relatively sharp back edge where the light has died down so that it's fading. And so you get, this sort of wave-like bubble expands through space. And exactly as Trevor says, if it hits something like a cloud of dust, then the dust cloud lights up. It's not possible just to see the light itself from the side. It's got to be illuminating something. And it's only when it illuminates something like a dust cloud that you see it. The classic example was supernova 1987A, which is in the Large Magellanic Cloud. It exploded in 1987. And about 3 years later, these two rings appeared around it, which turned out to be the front and back edges of a dust cloud that was actually in front of the supernova. So the lights, what we were seeing, we'd seen the direct light from the supernova, which had now faded away. But the light, what we didn't know was that there were these dust clouds actually in front of the supernova. And when the light reached them, it actually lit them up. And so we saw that. And the reason why you see it later is because the light is now taking a dogleg path from the supernova. It's not going in a straight line. It's bouncing off something. Yeah. And actually, it's a technique that I think is totally magical. In fact, I've got a whole chapter on it in Cosmic Chronicles. There's 2 plugs for books.
You're doing well today, Fred.
Yeah, I'll get another one in a minute as well. One thing that I think is fabulous is that you can, if the dust clouds are far enough away, then you get a significant time delay in the length of time between seeing the direct pulse of light from the supernova and the light echo. And the classic one is Tycho Brahe's supernova of 1572, which was observed again by its light echo a few years ago. So we saw the same light but reflected off a dust cloud. And that was fantastic because it meant that you could bring to bear all the modern instruments, the analytical instruments that that actually allow us to understand what's going on in a supernova, you could bring that to bear on the light that was reflected. And I'm going to correct myself, because it wasn't Tycho Brahe's supernova of 1572. It was Kepler's supernova of 1604.
Oh, right.
It was a different one, but it's still, 500 years ago, 400 years ago.
I was going to pick you up on that.
Yeah, I'm sure you were, yeah.
What and Trevor's assertion that the speed of light seems quite slow. What do you make of that?
Well, yeah, compared with the size of the universe, it is. So the light from the Big Bang itself, which we can still see, that's taken 13.8 billion years to get here, even though it's whizzing through space. But I tell you, 300,000 kilometers per second is pretty damn fast by any standards within the solar system.
Not as fast as teenage drivers can be sometimes.
Well, there's that too.
Yeah.
But yeah, notwithstanding that, it's pretty high speed.
Yeah, amazing. The other thing about light that intrigues me is we can't see it. We can only see what it does. Is that a fair assumption? I mean, it's like colour is an illusion, really.
Yeah, and colours in the sense that, you might see red differently from what I see it. But to a physicist, red is very specific. It's light with a specific wavelength or carrying a specific energy, if you want to put it that way. The two are equivalent. So, yes, it's only possible to see photons of light when they hit something.
Yeah.
When they interact with a different kind of subatomic particle. That's what it actually means in physics terms.
And the other thing that intrigues me is shadows. I mean, the photons hit something, so they don't go through it, and therefore a shadow is cast where the light doesn't go.
Yes, that's right.
We see it every day. We're so used to it. It's a natural part of being, but I still sometimes look at them and go, that's just weird. It's just weird.
Well, that's right. It is in many ways. I mean, I'm going to talk about shadows in a minute as well, but you only see a shadow if there's light around that's not hitting the object that's causing the shadow.
Yeah,
so
that's right.
It's a kind of double negative thing.
And the other thing is, of course, we see the light hitting the ground and the shadow from the object it's hitting that's behind us or something, but you've got to consider it on a global scale that there's also a shadow being cast beyond the Earth because that light is being blocked by a planet. I mean, it's freaky. It's really freaky. Yeah.
Indeed.
Does my mind in. Thank you, Trevor. That's a really good question and self-answered if you didn't figure that out. Now, let's move on to this is going to be fun. This comes from Oregon.
Hey, this is Nate from Oregon. So a friend of mine at work and I were laughing about flat Earth theories and just in general having a good laugh about it. I wanted to know what your guys' take on that is at a scientific level, because we all know it's obviously nonsense. And more importantly, being from Australia, what's it like walking upside down all the time? Thanks.
Thanks, Nate. Well, I'll tell you, I do get a bit dizzy occasionally and my nose runs backwards.
That's too much information.
Oh dear, yeah. Flat Earth theory. We have actually addressed this a few times. There are a few flat earthers that have got into arguments with our listeners, and people have come to us and said, "Look, how do we know? How do we know for sure that it's not flat?" Well, I think it was the Egyptians that initially figured it out. Wasn't it, Fred?
The Greeks certainly did.
The Greeks, yeah. Maybe it was the Greeks.
And they used shadows to do that. And it's exactly the shadow that you've just been talking about, the one that the Earth casts in space. The Earth casts a shadow. We don't normally see it until, as we were saying, the light hits something and the shadow and the light that the absence of light reveals the Earth's shadow. And that happens in an eclipse of the moon. And the bottom line is ancient people observed eclipses of the moon. They figured out what was going on because they knew the sun was on the other side of the sky. And what they observed was that the shadow of the Earth is always a circle. And the only thing that would always produce a circle is a sphere.
Yeah.
So that's how they knew it was spherical. And going to the question about what do we think scientifically of flat earthers, excuse me, they are really interesting scientifically, but it's more from the psychological point of view than anything to do with physics, because it is unmistakably the case that the Earth is not flat, that it's a spheroidal object, and it's demonstrated in almost every possible way. And to deny that is denying something that is a reality that everybody accepts. So it speaks of some really interesting psychological issues. And there was certainly an ABC science reporter recently went to a flat Earth conference, and he basically wrote it up as an interest in social behaviour and as an observation of social behaviour, the way people who have got a crazy idea but somebody else agrees with them, they've got this herd mentality, and you've got suddenly some really interesting psychology taking place, which can be quite dangerous in the wrong circumstances.
Yeah, they share the same department as the anti-vaxxers, I believe. But
maybe so.
You can understand the peoples of the past, the people of who historically believed the Earth was flat, because you'd go down to the beach and you'd look out over the horizon and there was a line, and you'd think, oh, that's the end of the Earth.
Yeah.
I mean, what else do you think?
Yeah, that's right. So, and you're right. Probably most people in ancient times thought the Earth was flat, but it was the what you might call the cognoscenti, the intellectuals of the time, who knew that it wasn't. There was an earlier, one in some ways even earlier example of people trying to figure out what shape the Earth was the fact that if you go a long way south, for example, you see different stars. And so that tells you at least that the Earth is cylindrical. But then, the eclipses tell you that it's actually a sphere.
And as we discussed once in an episode far, far back, if the Earth was flat, there would be times where the shadow of the Earth on the moon would be a line.
Yeah, that's right.
And that never happens.
Never happens.
Never. So there you have it, Nate, all sorted. And thanks for the question. That was a lot of fun. Sorry, go on.
I was just going to say, your nose running backwards because we're upside down. For me, the Earth's the right way up here.
Yeah, that's what I reckon.
But it is really interesting because so much of what we do in the world of astronomy is Northern Hemisphere biased. Like you look at a chart showing the phases of the moon, and even here in the Southern Hemisphere, they show them the way round that they appear in the Northern Hemisphere. So first quarter shows the illuminated bit of the moon on the right, whereas here in Australia, it's on the left.
Yeah.
Things of that sort.
Well, that's the thing. I took a photo of the moon the other day, which I put online, and it was actually a daytime photo. That's what I loved about it. I just sort of looked up and went, "Whoa! I'm going to take a photo of that with my little digital camera." Came out beautifully. So it's on our Facebook page, on the podcast group Facebook page, if you want to have a look at it. A few people have actually stolen it for their computer screens and for their mobile phone screens, which I'm fine with. Yeah, you could go for it. But I looked at that photo, and then that night I was watching a TV show, and they showed a photo, like a screenshot of the moon from the Northern Hemisphere, and it was exactly the same phase of the moon that I had taken a photo of, except it was flipped.
It's upside down.
Yeah.
That's right.
So, we're the right way up. Yeah. Yep. Okay. Thanks again for your question, Nate. Lovely to hear from you in Oregon. This is Space Nuts. Andrew Dunkley with Fred Watson.
3, 2, 1.
Space Nuts.
Now, if you are into social media, then you can find Space Nuts on Facebook. We have a dedicated Facebook page, but we're also available, for those who are listening to us on the community radio network across Australia, we're available as a podcast. which you may have picked up on in the first couple of episodes that have been broadcast. And we have a podcast group on Facebook. It's called the Space Nuts Podcast Group. And this is where people, surprisingly, this is where people can get together and talk to each other that listen to the show, talk about astronomy. Sometimes they compare the size of each other's telescopes, and they talk about things that are happening in the astronomical world. That recent hit on Jupiter that we talked about, somebody's actually done a post about that. I think it was "Thanks for taking one for the team, Jupiter," which I thought was a great line. It's a really fun group, and if you want to get involved, all you have to do is log in and join the Space Nuts Podcast Group on Facebook. And if you're a YouTuber, we're on YouTube as well, so you can see episodes of Space Nuts on YouTube. So just do a search in there for the Space Nuts podcast and you'll find it. And, of course, these days we're a radio show as well. So, it's good to have all these outlets where people can share astronomy and talk about what interests them. And right now that's going to be Gage in Huntsville.
Hey, Fred and Andrew. My name is Gage, and I'm an engineer from Huntsville, Alabama. I have a question regarding relativity, and this probably comes as a surprise, but y'all have discussed the effect of time dilation on objects moving near the speed of light. But I was wondering if we could slow down for just a minute. Theoretically, if there were an object not moving at all in the reference frame of the universe, would there be any effect on the object that can be proven by the general theory of relativity? I'm assuming that there would not, but I'm curious to hear your thoughts. Thank you guys for the wonderful podcast. I've been listening for years now, and I've enjoyed each and every one. Have a good one.
You too. Thanks, Gage. Love your name, by the way, Gage. It's got power. It's got strength.
It's good for an engineer too.
Yeah, it is. It's good. It's very good. Now, the effect on non-moving objects in relation to relativity. Have I got his thinking right?
Yeah. This question's about special relativity rather than general relativity.
Okay.
Special relativity is how things move and what happens to the space and time in which they move. So the bottom line is, so the question is, if you've got an object that's at rest relative to the reference frame of the universe, and that's a difficult thing to define because we don't have anything that really, is the 0 point of the universe in terms of its motion. But if we could define it, and you put an object there, if you were also at rest with respect to the reference frame of the universe, you wouldn't see any time dilation effects. It's only when we are moving with respect to the object itself that or the object is moving with respect to us, that you see these time dilation effects, which is why it's called relativity. It's how one moves relative to the other. So with just one object, no time dilation if you're in its reference frame, if you're looking at it the same speed that it's going, i.e. 0. But as soon as you're starting to move, and especially when you get to move near the speed of light, you will see time dilation effects. I don't know whether that answers the question really, but
I think it's been demonstrated in comic strips, like somebody standing still and a car passes them at the speed of light, or a train. They try to explain the effect of time dilation with that kind of demonstration. I still can't quite get my hand around it, but
well, it means that if you something whizzes past you, whether it's a train or a car or an aircraft, and it's travelling at nearly the speed of light, and assuming you had a means to observe it, which is another question, you would see their time as if it had slowed down. Whereas to them, the person who's moving at that speed, time is just passing normally. But it's the way it looks to you because of this relativity effect. And that's, it's a banal example to talk about trains and buses and cars and things. But at the rate at which things travel in the universe, it's important. And actually, I think the first time it was observed was when cosmic rays, this is before the war, I think, before the Second World War, so maybe in the 1930s, could have been the 40s. Anyway, some certain cosmic rays, which are subatomic particles that come from the universe, they are muons, they're called, and they have a very well-defined decay time. And it turns out that the muons coming down through the atmosphere from the universe take longer to decay because they're moving at nearly the speed of light. So we see time dilation, in action with phenomena like that.
Fascinating.
It's almost like a train going past, but not quite.
Yeah, I think we just use those kinds of objects because we can relate to them.
Yeah, we can. Actually, I think Einstein did too in one of his books, which is among those.
I learned something about Einstein this week. Did you know that he had what do you call it? He had what's called wild hair syndrome. And it was because he had that frizzy hair. Because there's a kid in the news that gets teased a lot and people pull her hair. She's 6 years old and she's got the same affliction. And apparently it's where the follicles, because of a DNA issue, grow in heart shapes instead of being round and make your hair uncontrollably explosive. Einstein had that affliction.
Yeah, it's a good affliction to have. It's not clear whether I've got it or not, but I suspect the answer is no.
Very hard to tell at the moment. All right. Thanks, Gage. Lovely to hear from you. Let's go to the Netherlands now.
Hi, Fred and Andrew. This is Aaron from the Netherlands. First off, you had a question from someone named Random. Random is actually the name of Arthur Dent and Trillian's daughter in the Hitchhiker's Guide to the Galaxy series. So that name makes perfect sense. I have a question about time and gravity, because they keep mentioning that time causes gravity. But if the gravitational constant is a constant, then and time is relative, wouldn't that mean that gravity causes time and not vice versa? So if nothing has a gravitational pull, then there wouldn't be any time either. Does that make sense? All right. Love the show. Bye.
Okay. Wow.
No, it's a good question. And I like the bit about random as well. I'd forgotten that.
Yeah,
it's a long time since I perused the Hitchhiker's Guide. Gravity and time are interlinked, but not in a causal way. Time is probably the least understood of all physical phenomena. We know that it behaves like a dimension in relativity. That came out of the special theory of relativity. But we can't manipulate it in any way. We really have very little understanding of it. We see the phenomena that are related to time, like cause and effect. Cause is always before effect, at least in the same reference frame. So where gravity and time do interact, it's with time dilation, gravitational time dilation. So, and you've got to have matter for that to happen. So matter is what distorts space and time, and causes the space to bend and gives us gravitational lenses and things like that. But it also causes time to dilate and to slow down. And so that's why we have phenomena like, I think you and I talked about a gamma ray burst not very long ago that took different paths round a black hole, an intervening black hole, and the time slowed down differently for each of those paths because it was going through a different bit of the gravitational effect of the black hole. And so there was a time delay in these blips arriving, the gamma ray burst. We still think the gravitational constant is a constant, but gravity is not, causing time. It can modify time. Perhaps that's the best way to put it, by the effect of matter on time dilation.
While you were talking, a question popped into my head. Of course, before the Big Bang, there was no time. Time started as soon as the Big Bang started. But has anyone actually been attributed with the discovery of time, or has it just become something we knew about?
Yeah, it's a bit like the naked eye planets. They've always been known. People have always recognised that not everything happens at once. Time is what stops everything happening at once.
So Fag didn't wake up one morning, walk out of his cave with his club and go,
it's tomorrow.
Hang on. looked at his wrist and went, I need a watch because I need to know what time it is.
Yeah.
I don't know.
That would have, yeah. Anyway, well, people did that with the sun early on. But no, it's as far as humans are concerned, it's something that's been recognised forever. I was just going to I was going to comment on what you said about the Big Bang Theory. And it's certainly true that the hot Big Bang Theory, which is built on the theory of relativity, does say that time starts with the Big Bang itself. But a lot of very eminent physicists have questioned that. Did time really kick off with the Big Bang? Was there a before? I think of people like Roger Penrose, whose theory of the universe, which is spawned from black holes. So you've got repeated universes being formed by black holes exploding.
Yeah,
and that needs time as an ongoing parameter. But the relativity theory, which is the best theory we've got to understand the universe, tells us that time started with the Big Bang itself. I'm happy with that because it means you don't have to worry about before, because if there was no time, there was no before.
There's another one that gets your head going.
Yeah.
My favourite thing about Big Bang Theory is Kaylee Cuoco. Yeah. Anyway.
Okay.
I'm pretty sure I'm not alone on that. But anyway, lovely to hear from you, Erin, and hope all is well. And that brings us to the end of another show. Thanks to everybody who's contributed this week. Really appreciate it. Still got quite a few questions to get through. Lots of text questions, but we're going to work our way through them. But yeah, thanks for joining us, and hope you've enjoyed the program. And we'll be back again next week. Now, don't forget, if you do want to get in touch with us, you can do that via our website, spacenutspodcast.com or spacenuts.io, whatever suits you. And there is an option on the right-hand side of the webpage where you can send your voice message, which is how you can send us audio questions. You can also go up the top and click on the AMA tab, because up there you can send us email questions as well as audio questions. So those are the two options for sending us questions, or just observations. People have sent us just comments that way too, which we've got no problem with. And while you're there, have a look around. Astronomy Daily sort of gives you regular updates of astronomical news, and you might want to become a patron. There's links in there about becoming a supporter of the show. And, of course, the Space Nuts shop, which has got all sorts of things in it, including the Space Nuts mug, Space Nuts stickers, Space Nuts, that's upside down, Space Nuts shirts, and just a whole bunch of books by this random bloke who just managed to hack the website and get them in there. I think his name's Fred. Anyway, go and have a look at spacenutspodcast.com. Fred, thanks once again. Always great fun. Nice to talk to you.
Thank you, Andrew. And I did say I'd get another mention of one of my books in, and here it comes. Space Warp goes to the printers today.
Oh, wonderful. Congratulations. That's great.
Hopefully all good.
And I have now recorded 17 chapters of the audio version of the Hitler Paradox. So that'll be out. At least it gives me something to do during lockdown.
Well, that's right.
Yeah.
Gets you out of mischief.
Yeah, I wish I hadn't picked so many nationalities amongst the characters, because
Are you doing the accents and everything?
I've chosen not to. It was just too big a challenge for my feeble mind. All right, Fred, catch you soon. Thanks a lot.
See you later. Bye for now.
Professor Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio who puts all the bells and whistles and tinsel on everything. And from me, Andrew Dunkley, thanks for your company. Look forward to you joining us again on the next episode in about a week or so. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.